All right, Steve, we saw this setup here earlier in the background. Tell us about what it is and what it does and how it can help us.
Okay, so we'll start off first with the high definition oscilloscope. It's the HDO, in this case 6104, and it's the mixed signal. So it's a 1 gigahertz scope that we're showing here, but they really start at 200 megahertz. But it's got 12-bit ADCs on them, so unlike 8 bits, when you're looking at small signals buried in large and you want to see clean, crisp waveforms and to be able to look at things like the saturation voltage while you're looking at the total online, the bus voltage, there's nothing like having true 12-bit hardware to give you that dynamic range to see all those details. So we're showing here the HDO oscilloscope. We're also showing a variety of probes that allow you to connect to your either an offline supply or a DC to DC or AC to DC or DC to AC inverter. So we have all the right probes for that. So I'm connected right now to a flyback, and you'll see here the typical, single MOSFET flyback. And then we also have a signal source to make sure that the propagation delay differences between probes get eliminated, and we have some tools to help do that. Also, fine adjust errors that come from like a current probe. You also want to reduce those so that your measurements are very accurate. So that's what we're showing here as well. I have a differential amplifier here off to our right,
which I'm hiding right now.
Yeah.
Right down here.
Right down there. Yes. And that is an excellent amplifier in that it also serves as a clamp. So when you're looking at offline supplies and you have high rail voltages, but you want to see a very small signal, this will clamp and will focus our 12-bit ADCs just on the saturation. Now we can take that and the current going through a MOSFET, and now we can make accurate conduction loss measurements. And then RDS on is so important, and how RDS on changes over time.
Since I have many hobbyists on my blog, can you explain real quick what RDS on is? And while we're at it, can you tell us what is the real advantage of a real 12-bit scope over high-res mode scopes that have been out forever?
Okay, great. So RDS on is when a switch, a MOSFET is on, it's not like a perfect contact. It does have some resistance, and that does change, especially with temperature. So under full loads, that resistance will change, and it's nice to plot that out on how that is actually changing. So you have resistance, it causes losses, and you need to quantify that to determine how efficient your power supply is going to be. So that's RDS on, and along with those losses, just a side comment too, we need to know the turn on transitional loss, the turn off transitional losses, because a device is not a perfect switch. We'd like it to be, but there are losses associated with it. So with RDS on, with the turn on and turn off transitional losses, and for a discontinuous power supply, the off state losses also, we want to verify that it's really zero, and so at any rate, so we have so that's a little bit on your first question. Mm-hmm. Your second question on the advantages of 12-bit, when you take a sample, and across the screen here, we're looking at 125,000 samples from left to right on every one of these waveforms. And by the way, this is VDS. This is the drain to source voltage across that MOSFET switch. This is the gate. Since this is a voltage-driven device, when you give it 0 to about 12 volts, that turns on the device. And so you can see it go from high voltage to 0, and then when the gate shuts off, then the voltage, instead of a short now, effectively, goes right up to hundreds of volts or whatever your rail voltages inside the power supply is. This is the current actually going through it. And so when the device is on, we're going to conduct and allow to charge in this MOSFET, the transformer inductor above the MOSFET, and that's what we're charging and discharging to the secondary or to the output after we filter it. So at any rate, we're looking at all that and the switching. This is voltage times current, so this is really the power waveform. And this is the turn on and turn off transitional losses. This is conduction loss. This is your off state. And then we have 3 cycles. So that's just a quick overview. All of this with 12 bits is and with a scope that's capturing these signals with 12 bits is excellent, because when you want to see the details of that ringing, how well did your device shut off and your snubber manage a device shutting off? What is that frequency? And gee, should you take that frequency and filter it out? Well, now you're going to start losing some efficiency, but you've got your power supply is less noisy. So you have to make these trade-offs, and with a 12-bit scope, the details in that waveform right there are very important. 8 bits, you can't see the clarity as you can with the 12 bits. And because we're using 12-bit ADCs in the scope, we, the manufacturer and designer of these scopes, has to have a signal path to that ADC that's very clean. So it's low noise, so you'll see that the waveforms will be cleaner, crisper. Lower noise with a low noise amplifier in front of the ADC means accuracy goes from 2 or 3% typical with 8-bit scopes is now 0.5% DC gain accuracy.
And my viewership actually knows the insides of the scope. We took a close look at the analog front end, no problem. It was very interesting to look at it.
Yeah,
but
great.
Carry on.
Yes, so that's pretty much the answers to your question. With 12 bits, by the way, you could add some more filtering, like other companies try to do to get it up to higher effective vertical dynamic range. We'll take a 12-bit and we can bring it up to 15 bits if you really want to see details of a waveform as well, and reduce some of the noise. And so we have the option that we can turn on and we can turn off, and we can add more effective bits in half-bit increments. So it's really cool.
So ERES isn't dead, it's just another step higher from what an 8-bit scope can do. By the way, one of the things I noticed when I first used the HDO is you see a lot of noise that you think must be oscilloscope noise, but it's not. You have to really transition to understand what you're seeing is actually in your signal. You have just not seen it before.
Yeah.
That was a little transition for me, but it was apparent if you change your parameters, the noise would change, so it couldn't be the scope. But I don't know if you had the same thing when you first played around with it, but I certainly had that.
Yes, I mean, first when I first looked at the 12-bit scope, I saw that with no signal going in, the baseline noise is so nice. It's so, and we shouldn't evaluate a scopes on baseline noise because you're not stressing the amplifiers. And so it's only when you have a signal going into a front end can you see what the amplifier of the scope is doing and how it's responding to the varying frequencies and step rise times and fall times. So that's one thing that we need to make sure that people understand, that evaluating the scope when you make a purchasing decision on the baseline noise it's like driving a car, testing the road noise by sitting in the parking lot. You can't tell. Let's take a look at the software tools. I had a lot of fun with our software design engineers that when we created this user interface, and I think users will find it to be pretty helpful to make accurate measurements, tools to help reduce sources of errors, and so I can just quickly do an overview.
Yeah, that'd be interesting.
Yeah. Well, actually, with LaCroix, we're going to do a look at analysis, and this is where we have different application software tools, and this is how you access them. And what we'll do is we'll focus on power analysis right now. So we'll come down to power analysis, and by the way, I'm using a mouse, but I could use the touch screen, and I also have access to the front panel. So there's like 3 ways you can drive this scope.
A really great feature, I think, is this touchscreen button that you can disable the touchscreen with, because I'm the kind of person that pokes around on the screen and wants to show stuff and screws up measurements, so I'm really glad I can disable that. And sometimes I get frustrated when I forget a button, I switch it off, but back to your presentation.
Yes, that's true. Yeah, you can go either way, and I have customers that go with, for a while they'll have it on, and other times they'll shut it off. So, okay, so when I pull down the analysis menu, what we come with is, with LaCroix, always go from left to right when you have a control dialog open, and as you make changes on the left, it'll change the menu items to the right. So for switch mode power application, we have 4 analysis types, and we have just a quick overview of it. Device, so when you're in this switching section of the power supply and you want to look at device losses, and when you want to look at turn on and turn on, transition losses, conduction loss, off-state losses, all of the losses across each cycle, and then accumulate those so that over time you can see how your losses are changing as the device heats up under load conditions or low load conditions. And so there's this section, it would be used for that. Also, safe operating area. Are you exceeding the voltage or current of a MOSFET or an IGBT? And there's tools to help with that. And BH curve and looking at the saturation of a magnetic device in circuit. This is where we have a quick setup on RDS-on and how a device turns on and off, which is DVDT or DIDT. So that's in the device analysis. In control loop, we're focused on time domain here. There's other companies that do open loop. You actually open the loop, and as you monitor the output of a power supply's voltage or current against a comparator, the difference, the error, is actually outputted to a controller IC, and that controls this gate on time. So the longer that the MOSFET's on, the more energy will be transferred over to the output. But you know what? You don't want that supply on and generating that much more unneeded energy, so the controller will notice that the error difference is very small, and it will actually shorten that on time of the gate, therefore transferring less heat, more efficient. So switch mode power supply designs are really good for efficiencies.
That's what it's all about, efficiency nowadays. Everyone wants to be green, and everyone needs the tools to be greener. That's just a big thing to go to. People pay a lot more just to be green. That's a good thing, I think.
Yes, for sure. So it's really important to control your control part of your power supply is set up. And so we do closed loop analysis, and we do time domain modulation analysis. So we'll trigger on a load change, and we'll look to see what the control loop's response time is, and whether the control design is underdamped or overdamped. How long does it settle to get a nice clean output again from a load? So this is a tool in time domain.
And that's a very important factor. You don't want your voltage to screw up when you change the load. And unfortunately, some cheap Chinese power supplies do that. And some people are not aware. They hook up their really sensitive devices to it. And you change the load by just switching it on or off. And all of a sudden, you're doing nasty stuff.
Oh, yeah, absolutely. Yep. So it's important to understand the capability of a control loop. Line power is a power quality power analyzer, if you will, that we brought into the scope. So you'll be able to capture the time domain voltage and current that the power supply is pulling, and you can look at its RMS voltage, RMS current, real power. What is the actual power of being pulled by the supply? Apparent power, which is important so that you know how to set your design and your margins. Power factor, how efficient is that power supply? Reactive, phase angle, and crest factor are also available. So this is in the line power, we're looking at power, but there's power quality. But we're also looking at harmonics. There are requirements. CE requires that under full load, that the power supply cannot emit frequencies, and that's defined for a class A, B, C, or D type power supply. So we've got that all set up for each of the classes, class A, B, C, or D, and we'll create a FFT display that shows for up to the 40th harmonic what is the current harmonics for each one of those, and do they exceed or pass for each of those harmonics.
Very nice, and as a European, I love that the standard frequency preset is 50 hertz.
That's right, yes. Yes, I've had a chance to work with European, Asian, and U.S. Environments, and we have to have our software to support all of that. Under performance is the last of the four analysis types, and here we're looking at efficiency and ripple. So the input power and output power. Right now, I'm not hooked up to anything that would look at efficiency.
Right.
And then there's ripple, which is very important to be able to look at the output of power supply and get to know how much noise is on that? What noise is coming from the switching modulation of the switching devices, and should you filter those out? And what should that output capacitor be? And so you need the right tools, you need the right probes, and you need to know the frequency content. So I've taken a spectrum analyzer, LaCroix's taken the spectrum analyzer software tool and brought some of those pieces into the power application so that you can look at the frequency domain of your ripple and see the content of that.
And that's something that makes particular sense with a 12-bit scope, because if you try the same with an 8-bit scope, you're really going to get trouble. I think power is a great example where 12-bit really shows its power, because you have, nice play on words by the way, because you have high voltages and small voltages on top of that which you want to measure, so you need the resolution that way, and it's a great application.
The frequency noise floor of an 8-bit versus the 12-bit, you'll see dramatic increases, so that you're much more sensitive and you can see much more details in your ripple measurements with a 12-bit scope.